We are going to talk more about Taylor and Maclaurin now, and you should be happy because we're coming to the end. We are on the last, I guess, 8 worksheets or so. We are going to do some cool things and apply what we've already learned about Taylor and Maclaurin. So I'm going to give you a sample question first to explain how you deal with question number 1. And then on the worksheet, 2 and 3 are very similar, and 4 has a different flavor. So I'll just go through them in that sequence. So a similar to question 1 would be the following question. Use a Taylor or Maclaurin series to compute the following limit. Limit as x goes to 0 of sine x minus x all over x cubed. And what you want to do is you want to expand sine of x here using what you know. Okay, so if we remember, the derivative of sine looks like this. Derivative of sine is cosine, derivative of that is negative sine, and then you get negative cosine and it repeats. And since we're centering it at 0, this causes us to get this series of terms, or coefficients rather, 0, 1, 0, negative 1, 0, 1, 0, negative 1. Okay, so what's going to happen is you're going to pick up the terms like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. I happen to know that's all I need. That's from experience. You may not know that that's where you can stop. Okay, so now what am I going to do? I'm going to say, hey, if I can do this expansion, the x's are gone. Now I'm going to go to the next stage, and I'm going to bring that x cubed right upstairs into that expansion. And so I get minus 1 over 3 factorial plus x squared over 5 factorial minus x to the 4th, I guess, over 7 factorial. It just continues. Everything downstream is going to go to 0. Okay? And so that means our final limit is just going to be minus 1/6. And if you want to verify that you're not completely nuts, why don't you just pull up some technology. Now, even though this isn't a proof, you expect that the technology probably does a pretty good job, although when we zoom in we might get weird effects, but probably not. Desmos is pretty smart. So here's 0 to negative 1. That looks like it could be, let's see, there's a half. That looks like a third of a half. That looks about right. So it's not going to tell you exactly if you're right, but it's going to give you a pretty good guess. And if you're completely wrong, it'll give you a good hint about that. Okay, now for the question 2, question 3 type of things on this worksheet, I want you to feel free to use help from a friend, let's say. This is a good website. I just Googled common Taylor Maclaurin series and I took the top hit. But the reason I took the top hit is it looked like it was at a school. So I'm not going to go to some place I don't recognize. I don't know what MATH222.net is. It may or may not be right. Wolfram is okay. I don't know most of these sites, but Wolfram is safe. Most educational sites are going to be safe. Just look. More than likely, it won't be what you want. But in this case, it is correct and it is what you want. And you don't have to read most of what this instructor wrote. Everything you need to do your homework is on the first page. It's a nice reference for the most commonly used Taylor or Maclaurin series. He just sort of he or she just bundled them all as Taylor, because if you're just going to be generic, you can just call them Taylor. Okay, so we want to do these exercises that are asking us, please find the sum of the series. So let me give you one that I'm just making up that's of the same type. Okay, a different question that's similar to the things you're going to be doing on your worksheet. So you're given some kind of sequence and you're like, oh my gosh, what is this? Well, the point we're making here is this arises from some Taylor and Maclaurin. This does not look shifted, so I'm assuming it's centered at 0. Okay, so we can go ahead and use Maclaurin. and it's going to be x to the n over n factorial. Now, so the first step is to rewrite the problem and put this little piece on the end to just get your brain thinking right. Okay? And then we're going to play match the pieces. Match the pieces. So what I'm looking at is something is going up, up, up. And I'm noticing that I could just write this as, I could just write this as 1/3 and then square it instead of squaring the denominator, right? So I could cube this, and that's in fact what I'm going to do, so that I can assume that x is equal to 1/3. Now, what pieces have we taken care of? We've taken care of all that. The x to the n's we've taken care of just by saying x is 1/3. Now, what it's telling us is the rest of this mess has to equal to 1 in order to make the pieces match up. Okay, but that's in the denominator, which means the nth derivative at 0 of our function has to actually be equal to n factorial. And you're like, oh my gosh, like what does that? I don't know. Okay, I don't know what does that. I mean, I do, but I'm pretending like I don't because maybe I forgot. Now, you're going to write this generally, which I just did, and for a n, so a n is equal to fn of 0 over n factorial, and that equals to 1. So I wrote that generally, and I went one step further in this process. I'm actually trying to solve, and you may recognize it sooner or later. You may not. So the fourth step is to write out some pieces. Write out pieces. And in this case, we know we can create another Maclaurin series. We can say f is equal to, let's see, 1 plus, this must be x plus x squared plus x cubed, because with each of these pieces it would be x to the n over n factorial times n factorial to make those cancel, right? So this is what's happening. You're just generally getting x to the n's, and now you look it up. Now you look it up. Step 5, so I'm going to go right on over to my little friend's website and say, what is this animal? And I'm like, oh yeah, I forgot that that did that. 1 over 1 minus x. How about that? It was sitting there. So f equals 1 over 1 minus x. Now, step 6, I just plug in x and you're done. So we said x is 1/3, right? So this is equal to 1 over 1 minus 1/3, which is 1 over 2/3, which is 3/2. Okay? So, so that's great. So you just rewrite it, match the pieces, find some general expression. You might have to write out some pieces again so that you can look it up. Once you find out what function this whole thing is based off of, you can just plug in x. Now you may have been able to leapfrog from this stage to this stage. That's okay too. If you can see, oh wait, that's just a progression of x, x squared, x cubed, and you look it up, that's fine. You can jump over that step. So I'm giving you all the steps you might need, but you can leapfrog over them if you wish. Question 3 is very much like question 2, even though it's stated differently. So in question 3, the x's are written out explicitly, and then there's a thing on the right-hand side. So it's actually somehow easier than question 2 because you see the x's. So you just still harness that lookup table. You just go ahead and look it up, and then you can take it from there. Okay, and finally, my advice on question 4. I can't actually give you a hint on question 4 because it's too easy. So I'm just going to break down the steps a little further for you. I'm going to use x instead of theta because I just don't like the theta. Okay, so e to the x equals what? So go ahead and write out your Taylor, well, it's actually Maclaurin. Write it out for yourself. Sine of x, same thing, write it out. Cosine of x, write it out. So that's step one, is just gather the pieces you need to do this problem. These you can either look up or figure out from first principles. You should use this opportunity to probably do both. But if you're just being lazy, at least just look it up and then go to the next step. Okay, step 2 is replace this x here, bing, replace it with I times x, or I times theta if you want to use the theta. Okay, replace every instance of x with I times x. And then if you get, for example, ix squared, that is I squared x squared, that still works. But I squared is -1, right? Because I squared is equal to -1. I cubed is -I, and I to the 4th is just 1. Okay, so you do those substitutions, and then you should get a change over here. Okay, this bit is going to change. Now, the next thing you want to do is you want to multiply sine of x by I. That's really easy. So you just take sine of x, and every single term you just put an I in it. And that's really, really easy. Okay, then the next thing you want to do is you want to add these guys. And at this point, you're not even going to have to physically do it. You're just going to look at it because they're going to be sitting there on the page and you will have scribbled all over your page. Okay, and then step 5 is just compare. Because at this point, you probably don't need to write anything. It'll be obvious to you why this bit is the sum of these guys. Okay, so if you were writing it up formally, of course, there'd be a lot of cutting and pasting and whatnot, but you don't need to formally write this up. I just want you to understand how all these pieces fit together, so it doesn't matter if your page is a gobbledygook mess, as long as you comprehend how all the pieces are fitting together, so you could field a potential question on it, okay? That should take you through worksheet 30. I will see you around. Bye.